All right, let's get right into it. Microcontrollers are incredible, right? They're the digital brains inside basically everything, but they have to live and work in our very analog world. So this explainer is all about that connection, how we build the bridge between these two realms so a microcontroller can actually sense and react to things like temperature, pressure, or any other physical variable you can think of.
And that brings us to the fundamental problem. A microcontroller's entire world is just ones and zeros. It's all discrete. Black and white, on or off. But the real world we want to measure, it's not like that at all. It's continuous. The temperature in a room doesn't just jump from 20 degrees to 21. It flows through every single value in between. So how on earth do we translate that smooth, continuous reality into the rigid, step-by-step language a computer can actually understand?
Here's how we're going to tackle that. We're going to follow the entire journey of a signal. First, we'll get a handle on the two worlds we're trying to connect. Then, we'll look at how a microcontroller listens to the world using something called an ADC. After that, we'll see how to clean up that signal with an op-amp, and finally how it talks back using a DAC, before we pull the whole system together at the end.
So let's make sure we're all on the same page. An analog signal is basically a continuous wave. Imagine a voltage from a sensor. It could be 1.1 volts, or 1.11, or even 1.112 volts. It's infinitely smooth. A digital signal, though, is the total opposite. It's discrete. It can only be a series of specific numbers. For a microcontroller to make any sense of that smooth sensor reading, it first has to chop it up and convert it into one of those specific digital values.
And the crucial piece of hardware that does this translation is the analog to digital converter, or ADC for short. You can think of it as the microcontroller's ear. It takes a snapshot of a real-world voltage at a single moment in time and assigns a binary number to it. The great thing is, a lot of microcontrollers, like the PICs, have these built right into the chip.
So let's zoom in a little on how this listening process actually works. The quality of this whole translation from analog to digital really hinges on one key factor: resolution. And that resolution determines just how precisely our microcontroller can see the original analog signal.
Now this is where it gets really interesting. A small change in the number of bits makes a huge difference in accuracy. An 8-bit ADC, for example, divides a voltage range into 256 distinct steps. But just by going up to a 10-bit ADC, you get 1,024 steps. That's 4 times the precision. So why does that matter? Well, think about a digital thermostat. With an 8-bit ADC, it might only see temperature in chunky half-degree increments. Your room is always going to be a little too hot or a little too cold. But with a 10-bit ADC, it can see much finer changes, which means it can keep the temperature perfectly stable. So the bottom line is, more bits means a much more faithful digital picture of the analog world.
And here's what that looks like in a practical circuit. See that potentiometer on the left, labeled RV2? For our purposes, that's acting as our simple analog sensor. As you turn the knob, it outputs a continuously changing voltage. Now follow that line over to pin 2 of the big microcontroller chip. That's our analog input, AN0. From there, the ADC that's inside the chip takes over, converting that voltage into a number that the processor can actually work with.
So this conversion process isn't just one magic step. It's actually a sequence of operations that you control. First, you have to tell it which analog channel to read, since one ADC can often listen to multiple pins. Then, you set the speed of the conversion. A special sample and hold circuit then freezes the input voltage for a split second to make sure you get a stable reading. Then you kick off the conversion by setting a go bit. When the hardware is finished, that bit gets cleared, signaling that it's done. Finally, that brand new digital number gets stored in a couple of special registers, in this case ADRESH and ADRESL, and it's ready for your code to grab it.
But here's the thing. What if the signal coming from your sensor isn't perfect? What if it's super weak? Or maybe its voltage range doesn't line up with what the ADC is expecting? You know, in the real world, raw signals are almost never perfect. And that's exactly why we often need to condition them, to amplify them, filter them, or shift them before they ever get to the microcontroller.
And this is where our best friend, the operational amplifier, or op-amp, comes into play. Now, this schematic might look a little intense, but really it's just showing a few different ways to use the same basic building block. See up top the inverting amp and non-inverting amp? Those are both just used to boost a weak signal up to a level the microcontroller can read easily. Then you have things like a summing amp, which can actually add signals together. The key takeaway here is that we use these simple op-amp circuits to prep the signal before the ADC even lays eyes on it.
Now, op-amps can seem a bit like black magic.
But their behavior gets a lot simpler if we just assume they're ideal. These golden rules make analyzing a circuit so much easier. For instance, by assuming that no current flows into the input pins and that the voltage between those two pins is zero, we can figure out exactly how the circuit will behave just by looking at the external resistors. And for most real-world applications, this ideal model is more than accurate enough.
Let's just grab one solid example, the inverting amplifier. Its function is beautifully simple, and it's all defined by that one little formula. The output voltage is just the input voltage multiplied by the ratio of two resistors, RF and R1. It's that easy. So if you want to amplify a signal by 10 times, you just make RF 10 times bigger than R1. It's a simple, super predictable, and really powerful way to control your signal strength.
Op-amps can also be used for straight-up decision-making. A comparator doesn't really amplify a signal in a smooth, linear way. It just compares two voltages and tells you which one is bigger. This is absolutely perfect for things like a low battery warning. You just set one input to a fixed threshold, like 3.0 volts. The other input reads the actual battery voltage. The second that battery drops below 3.0 volts, the comparator's output flips, and the microcontroller gets a simple digital alert. It's time to turn on that warning light.
Okay, so we've successfully read and processed an analog signal. We've got the listening part down. But what about the other direction? How does our microcontroller take its digital calculations and use them to control something in the analog world, like the speed of a motor or the brightness of a light?
For that, we need the ADC's counterpart, the digital-to-analog converter, or DAC. If the ADC is the microcontroller's ear, then the DAC is its voice. It takes a binary number from the processor and generates a proportional, real-world analog voltage or current. And just like with the ADC, the more bits the DAC has, the smoother and more precise its output is going to be.
This circuit here shows two common types of DACs. Over on the left, the DAC 0808 is a parallel DAC. See all those wires? It needs 8 separate data lines to get an 8-bit number from the microcontroller all at once. But on the right, the MCP 4921 is a serial DAC. It's a lot more efficient. It gets that same data 1 bit at a time over just a few wires, which saves a ton of valuable pins on your microcontroller. But in the end, they both do the same job, turn a number into a voltage.
And here is the payoff. What you're looking at on this oscilloscope is a perfect analog sawtooth wave. But here's the cool part. This smooth, rising voltage wasn't created by a traditional analog circuit. It was generated entirely by a digital process. The microcontroller is just running a simple loop, sending a number to the DAC that counts up over and over again. This kind of precise, digitally controlled signal is essential for all sorts of things, like generating audio tones or controlling laser scanners.
Okay, now we can finally put all the pieces together. We've seen how to get information into the microcontroller from the analog world, and we've seen how to send commands back out. This creates a complete feedback loop, and that's what allows a microcontroller to intelligently interact with its environment.
So let's trace that signal journey one last time. Some physical event happens, a temperature changes, a button is pressed, a sensor creates a raw analog signal. An op-amp cleans it up and scales it. The ADC digitizes it. The microcontroller's code analyzes that number and makes a decision. It then sends a new digital number to a DAC. The DAC creates a new analog signal to control a motor, or a valve, or an LED, and that changes the physical world. That right there, that is the very essence of mechatronics and embedded systems.
Look, understanding this bridge from analog to digital and back again is absolutely fundamental to pretty much all modern technology. It's in everything from a simple thermostat that's reading a room's temperature to control a heater to a complex robot that's sensing its surroundings to move its motors. The principles are exactly the same. So the only real question left is, now that you know how it works, what are you going to build with it?